This slide outlines the essential security properties that must be upheld in autonomous vehicles. Confidentiality. Sensitive information, such as driver data and vehicle status, must be protected from unauthorized disclosure. This maintains privacy and prevents misuse of information. Integrity. The data and software within the vehicle must be accurate and complete. This ensures that the vehicle is operating based on correct information and prevents malicious tampering. Availability. The vehicle systems and services must be accessible and operational when needed. This includes the ability to perform critical functions like braking and steering. Authentication. The system must verify the identity of users and devices to prevent unauthorized access and control. This helps protect against unauthorized actions and data breaches. User privacy. Protecting user data is paramount. Personal information collected by the vehicle must be handled responsibly and securely to build trust. The image provides a visual representation of the complex security landscape in autonomous vehicles. It highlights the interconnectedness of various components and the potential vulnerabilities that need to be addressed to ensure the safety and security of these systems. It also illustrates how different security properties are relevant to different components and attack types. For instance, authentication is crucial for keyless entry systems, while confidentiality is essential for protecting data transmitted over wireless interfaces. Controller area network-related attacks. The CAN bus, while efficient, has inherent security vulnerabilities. Key challenges include a lack of authentication, meaning any device can join the network, and a lack of sender identification, making it difficult to verify message origins. The CAN bus also lacks effective error handling and network segmentation, making it susceptible to various attacks. Attackers can exploit these weaknesses through methods like bus-off attacks, which disrupt network communication, and schedule-based attacks that exploit predictable message patterns. In addition, eavesdropping, data injection, and denial of service attacks pose significant threats to the security and integrity of the CAN bus. In the coming slides, we briefly look at some demonstrated attacks. Bus-off attack exploits a vulnerability in the CAN bus's error handling mechanism. By intentionally triggering error counters in a target ECU, an attacker can force it into a bus-off state. This prevents the ECU from communicating on the bus, disrupting critical vehicle functions. To successfully execute this attack, the attacker needs to craft messages with specific characteristics that align with the target ECU's communication pattern. The figure on the right illustrates the CAN bus error handling mechanism being exploited by an attacker to send an ECU into bus-off. Persistent errors lead to the error passive and eventually bus-off. By relying on a unique preceded message, however, several instances of the victim might go untargeted by the attacker. We illustrate with the example shown. We have a victim message with a period of 10 and 9 odd messages with a period of 70. The victim message MV here has 7 instances, of which 5 are preceded by distinct messages, M2, M3, M5, M6 and M8. By using only one preceded ID, the attacker can target at most one instance of the victim in a hyperperiod. This increases the attacker's burden to succeed because the missed opportunities result in successful transmission for the victim ECU and allow the victim ECU to recover its TEC. To successfully execute a bus-off attack, an attacker must carefully synchronize their actions with the victim's message transmission. This involves crafting a message with the same ID as the victim's message and transmitting it simultaneously. By causing repeated transmission errors for the victim, the attacker aims to force the victim's error counter to exceed the threshold, ultimately leading to a bus-off state. Although the attacker can see the victim message content, the attacker does not know the exact time at which the victim message is released because each transmission of the victim can encounter release jitter, blocking by a lower priority message which may have started transmission before the victim, or interference from one or more higher priority messages. So based on its observation of the CAN trace, the attacker must estimate the parameters of the CAN message set. We use a greedy algorithm to accomplish this task. Using each transmission, the algorithm works backwards to estimate possible release time of the message. With successive transmissions, the upper and lower bounds of the message's period are established. These bounds are tightened until the difference between both is less than a single bit's transmission time. Once all parameters have been estimated, the adversary moves the second stage of the attack. First step in this stage consists of identifying and recording patterns. An attack pattern is a message sequence that the attacker can use to synchronize with the victim message, such as a series of one or more consecutive high-priority messages immediately followed by the victim message. A single lower-priority message immediately followed by the victim message. To record the timings of the patterns, the attacker starts a timer and classifies each message observed as high, low, or victim. Then it checks its observation to identify if an attack pattern has been transmitted. As soon as the attacker spots one of those patterns, it computes its future arrival and completion times and saves them. The attacker records each pattern. We use two timers, T-high and T-low. They are used to record the future starting time and ending time of the pattern so that the attacker can know when a certain pattern will occur in the future. T-high is started once a higher priority message starts transmission. It is invalidated if the higher priority message is followed by idle time or a lower priority message. The schedule-based attack can be further optimized using one of the following methods. Method 1. Average starting time. For each attack opportunity identified by algorithm 1, the attacker can compute the average starting time of that attack opportunity over n hyperperiods, regardless of the attack types. Method 2. Intersection of transmission times. In this method, regardless of the attack type, the adversary computes the intersection between the attack surfaces obtained over n hyperperiods for the kth instance of the victim message. In this method, if the intersection interval is empty, namely, there is no intersection between the attack surfaces of the n observations, then the attacker will not consider attacking that instance of the victim message and will treat that instance as an attack type. Method 3. Average of mid-transmission times. In this method, for each attack pattern of victim instance k, the attacker computes the midpoint of the transmission time for the preceding messages in the attack pattern. Then the average of these is taken over the n hyperperiods observed, again, regardless of variations in the attack types. The schedule exploitation stage is identical to the traditional boss-off attack, except that in the case of the schedule-based attack, the attacker has the ability to synchronize with multiple messages, thereby potentially reducing the time it takes to send the victim to error passive and boss-off states. CAN message injection attack. The figure depicts a man-in-the-middle attack on a CAN bus. An attacker intercepts communication between two electronic control units on the CAN bus. The attacker can then modify the intercepted messages or inject entirely new messages to manipulate the vehicle's behavior. This type of attack can have serious consequences, such as causing the engine to stall or the brakes to fail. Eavesdropping is a significant threat to the security of CAN bus systems. Attackers can passively capture sensitive data transmitted on the bus without being detected. This information includes engine data, sensor readings, driver inputs, diagnostic codes, and even navigation details. The stolen data can be used for various malicious purposes, including privacy violations, planning future attacks, and potentially compromising vehicle safety. Eavesdropping techniques range from simple bus monitoring to more sophisticated methods that target specific messages or exploit vulnerabilities in the vehicle systems. The illustration showcases a car computer system or ECU connected to a CAN bus. An attacker with a laptop and a CAN sniffing device is eavesdropping on the data transmissions traveling through the CAN bus. This eavesdropping can capture sensitive information such as sensor readings, engine control signals, and even driver inputs. Preventing eavesdropping on CAN bus systems presents several challenges. Implementing strong security measures like encryption and authentication can impact performance due to increased processing overhead, especially on resource-constrained ECUs. Retrofitting existing vehicles with these measures can also be costly and complex. To mitigate these challenges, we can employ strategies such as CAN bus encryption, message authentication, network segmentation, and intrusion detection systems. Denial of service. DOS attacks aim to disrupt normal vehicle operation by overwhelming the CAN bus. By flooding the network with excessive traffic, attackers can prevent critical messages from being transmitted. This can lead to engine control malfunctions, steering or braking issues, sensor data corruption, and communication breakdowns between essential ECUs. Techniques like frame flooding, high-priority frame spamming, node spoofing, and inducing bus errors are commonly employed by attackers to achieve this goal. Preventing those attacks on CAN bus systems is challenging due to real-time constraints and the need to balance security with low-latency communication. Differentiating between legitimate high message rates and malicious attacks is also difficult. To mitigate these challenges, we can employ several strategies. Intrusion detection systems can monitor network traffic for suspicious activity and trigger countermeasures. Rate limiting helps prevent network flooding by limiting message rates. Prioritizing critical messages ensures timely delivery of essential data. CAN bus segmentation can isolate attacks to specific segments. Regular software updates and security hardening for ECUs are also crucial for overall system resilience. Beyond the traditional attacks we've discussed, there are other vulnerabilities in the CAN bus. Due to its broadcast nature, anyone with access can eavesdrop on all messages, allowing attackers to learn ECU behavior and potentially impersonate them. This lack of authentication and limited message size makes it easy for attackers to modify or fabricate messages, injecting false information into the system and causing ECUs to malfunction. Sybil attacks and replay attacks also pose significant threats to the CAN bus. Sybil attacks exploit the lack of strong authentication on the CAN bus, allowing attackers to create multiple virtual identities and disrupt network operations. Replay attacks involve capturing and retransmitting legitimate messages to manipulate vehicle systems. Both types of attacks can lead to system instability, data corruption, and potential safety hazards. Perception subsystems, including radar, LiDAR, cameras, and other sensors, are critical for autonomous vehicle operation. However, they also represent significant attack surfaces. Malicious actors can manipulate sensor data to mislead the vehicle, leading to spoofing and eavesdropping attacks. The limited security features of the CAN bus and potential remote access points further exacerbate these vulnerabilities. To mitigate risks, we need to regularly monitor sensor health and implement robust encryption while also considering the broader attack surface of the vehicle. In the following slides, we describe a few of these attacks. LiDAR, a critical component in autonomous vehicles, is vulnerable to replay attacks. Attackers can record real LiDAR data and replay it later, misleading the vehicle about its location. This attack can be executed by introducing a random delay to the replayed data. However, detecting these attacks is relatively straightforward due to the sudden changes in pose measurements caused by the replayed data. LiDAR and radar jamming attacks target the core of an autonomous vehicle's perception system. By injecting false sensor data onto the CAN bus, attackers can create virtual objects, manipulate real object data, and disrupt the vehicle's understanding of its environment. This can lead to navigation errors, system malfunctions, and ultimately, increase the risk of accidents. Protecting LiDAR and radar systems from jamming and replay attacks is challenging. Implementing robust security measures like encryption and authentication can impact performance and add complexity, especially on resource-constrained ECUs. Retrofitting older vehicles with these measures is also difficult. To mitigate these challenges, we need a multi-layered approach. Encrypting CAN bus messages, implementing message authentication, and using intrusion detection systems can help prevent attacks. Regular software updates and restricting physical access to the vehicle's network are also essential for maintaining security. LiDAR and radar confusion attacks target the sensor fusion process in autonomous vehicles. By injecting false sensor data onto the CAN bus, attackers can create misleading perceptions of the environment. This can lead to navigation errors, incorrect path planning, missed obstacles, system malfunctions, and increased accident risks. The attack involves gaining access to the CAN bus, injecting spoofed sensor data, and manipulating the vehicle's understanding of its surroundings. LiDAR/radar confusion presents significant technical challenges for adversaries. They must understand sensor data formats and precisely time their spoofed messages to be effective. Also, modern vehicles often have intrusion detection systems, making it difficult to bypass defenses. To counter and enhance the resilience of LiDAR and radar systems against these attacks, we can combine the following measures. First, encryption and authentication can be used to protect data integrity, while intrusion detection systems can monitor for suspicious activity in the vehicle. In addition, regular software updates and physical access controls can further strengthen vehicle security. Autonomous vehicles heavily rely on GPS to obtain signals for localization, path planning, and also real-time messaging in their environment. In the figure shown, multiple satellites transmit GPS signals to the vehicle, providing location data. However, in a spoofing attack, an attacker can interfere with these signals by transmitting false GPS signals. This can mislead the vehicle's navigation system, potentially causing it to deviate from its intended path or make incorrect decisions. We also have the location trailing attack. This is a privacy concern for autonomous vehicles. This attack also uses the GPS signals. However, in this case, the attacker's goal is to collect the localization of the vehicle over a certain period of time. Upon processing this data, the attacker can then discover certain patterns about the vehicle and consequently about its driver. For example, by inferring a consistent location for the beginning and ending of the trips taken throughout the work week, the attacker might be able to infer the home and/or the workplace of the driver. In the figure shown, the attacker collected the data from a magnetometer sensor through an application that would not need any permission to have access to such data. These types of applications could be disguised as games or harmless applications downloaded by the user. Once the record is processed, a mapping tool can be used to infer the route of the vehicle. GPS jamming attacks target the accuracy of vehicle navigation by disrupting or manipulating GPS signals. Attackers can gain access to the CAN bus to inject false GPS data, misleading the vehicle's position estimation and disrupting path planning. This can lead to navigation errors, safety hazards, and even system failures. To counter these attacks, we need redundant navigation systems, robust GPS signal integrity checks, and ongoing research into anti-jamming technologies. Combining GPS data with other sensors and utilizing machine learning for anomaly detection can also improve the resilience of navigation systems. Beyond jamming and spoofing, GPS systems can be targeted by false data injection attacks, where attackers manipulate location data directly. Additionally, GPS denial-of-service attacks aim to completely block the GPS signal, preventing the vehicle from receiving any location information. Map server poisoning is a serious threat to navigation systems. By compromising map servers, attackers can modify road data, leading to incorrect routes and potential safety hazards. This type of attack can cause significant disruptions, including delays, missed turns, and increased risk of accidents. Malware injection attacks target the ECUs within a vehicle. By introducing malicious code onto the CAN bus, attackers can gain control over vehicle functions, leading to safety hazards, privacy breaches, and financial losses. This type of attack can disrupt critical systems, steal sensitive data, and potentially spread to other ECUs, causing widespread damage. CAN-based malware poses significant threats to vehicle security. Logic bombs, worms, ransomware, and spyware are common types of malicious software that can infect ECUs. These attacks can lead to various consequences, including vehicle control loss, data theft, and financial loss. However, the resource-constrained nature of ECUs and the complexities of CAN bus communication present challenges for malware development and execution. Now, having discussed these attacks, let's now look at some countermeasures that can help protect autonomous vehicles. Message authentication is crucial for protecting CAN bus communications from masquerade attacks. It verifies both the message source and its integrity. However, implementing strong authentication on resource-constrained ECUs presents challenges. Cryptographic methods like MACs offer solutions but increase computational load. Additionally, existing vehicles might require hardware modifications for deployment. Balancing security needs with performance and compatibility is essential for effective authentication in CAN bus environments. Device fingerprinting is a security technique that creates unique identifiers for network devices, similar to human fingerprints. ECU fingerprinting is a technique for identifying individual ECUs based on their unique characteristics. It leverages hardware variations like manufacturing differences and component aging to create a unique fingerprint for each ECU. By analyzing network traffic and device configurations, we can extract these fingerprints. This information can be used to build an intrusion detection system that operates at the physical layer of the CAN bus. By comparing observed fingerprints with known profiles, we can identify unauthorized or anomalous devices, enhancing the security of the network. ECU fingerprinting can help detect unauthorized devices and prevent impersonation attacks. While effective in many cases, ECU fingerprinting has limitations. It is vulnerable to masquerade attacks using compromised ECUs and requires regular updates to account for fingerprint degradation over time. In addition, the high computational demands for accurate fingerprinting can be a challenge. Now let's look at a few known fingerprinting techniques. Clock-based IDS analyzes message timing patterns to identify ECUs based on clock skews. Voltage-based attacker identification uses voltage measurements to detect anomalies. Voltage IDS focuses on analyzing unique electrical characteristics of CAN signals. Session extracts fingerprints from CAN frames for sender identification. Simple leverages single-frame analysis for real-time intrusion detection. Finally, a combination of voltage-based analysis and machine learning can improve fingerprint accuracy and reduce computational load. These techniques offer varying levels of accuracy, computational efficiency, and resistance to different attack types. The specification-based intrusion prevention system is designed to counter impersonation attacks on the CAN bus. The system utilizes an intrusion detection system to monitor for malicious messages and triggers a reboot of compromised ECUs as a countermeasure. By monitoring error frames and tracking error counters, the system can detect and isolate compromised nodes, preventing them from further disrupting the network. The effectiveness of this approach depends on the accuracy of the error detection mechanism and the ability to reliably identify compromised nodes. We can distinguish two types of specification-based intrusion prevention systems: message interval IDS and message response time IDS. A message interval IDS is a countermeasure that focuses on detecting message injection attacks by analyzing the time intervals between messages with identical IDs. It computes the time difference between consecutive messages and compares it to a predefined normal range. Messages with unusually short intervals are flagged as potential injections. This technique is simple to implement. This method might not be effective against attacks that carefully mimic normal message timing. In contrast, Message response time IDS focuses on analyzing the timing patterns of CAN messages to detect anomalies. By establishing expected response times for specific messages and monitoring for deviations, this approach can identify potential attacks. This technique is more complex to implement than message interval IDS, but it relies on accurate estimation of message parameters and might struggle with highly dynamic message sets. Information theory provides a foundation for anomaly detection in network traffic. By measuring the entropy or randomness of data, we can identify deviations from normal patterns, which may indicate malicious activity. This approach, known as entropy-based anomaly detection, is particularly effective in networks with predictable traffic patterns like IVNs. However, it has limitations in detecting low-volume attacks or content-based attacks like masquerading. To complement entropy-based detection, Bloom filters can be used to efficiently identify modified or replayed CAN messages. This approach offers a different perspective on detecting anomalies in network traffic. Machine learning offers a powerful approach to detecting unknown attacks in IVN environments. Both supervised and unsupervised learning techniques can be applied. Traditional methods like SVM, decision trees, and neural networks have been used, but deep learning with its ability to handle complex data shows great promise. However, high computational power is required. Combining multiple models through ensemble methods can improve accuracy and robustness. Machine learning offers significant advantages for intrusion detection systems in connected autonomous vehicles. By analyzing vast amounts of sensor data, ML-based models can improve accuracy and performance over time. Techniques like CNNKF, DSS, and MSOSTEM-CNN have shown promising results in detecting anomalies and classifying sensor data. These models contribute to enhancing vehicle safety by reducing the risk of accidents caused by erroneous data.